Now let's imagine we've got an object, a block here, on an inclined plane. So imagine we've got some tilted surface, and we'll assume it's tilted, say, 10 degrees from the horizontal. And let's imagine our mass is 12.5 kilograms. To start with, let's imagine that it's frictionless. There's no friction. We'll add some friction in later on. Let's see what's going to happen. Well, let's see. This is a little bit difficult because always before we had looked at forces in the horizontal direction and forces in the vertical direction. Should we do that now? Well, what we're going to do is actually break these forces down a little bit differently. One thing we know, if this block is going to move, it's going to move along the incline. It's only going to move, say, in this direction. It's not going to move in a perpendicular direction. Well, if it's not going to move in a perpendicular direction, we know that the net forces in that direction must be zero. So let's break it down into two directions, along the incline and perpendicular to the incline, because we know if there's going to be any motion at all, it's going to be along the incline and not perpendicular to the incline. So that's going to make it a little bit easier for us to solve the problem. What that means is we're going to define our coordinate system so that x is pointing along the incline, and we'll just say in a downward direction, because if there's any motion we know it's going to be down that way for this problem. And perpendicular to that, perpendicular to the incline, we'll define that as our y direction. Okay, very, very good. Now, what forces are acting on the mass? And again, remember, we are assuming there's no friction. So what forces are there? Well, there's weight. We know that there's weight. Let me get this off of there because I don't want us to confuse that with a force. All right, there we go. So what forces are there? There's weight. Weight is in what direction? It's always straight down. So here's the weight. And how big is the weight? We know the weight is always mg, which is going to be, so let me put it down here. Weight is always mg, which is 12.5 kilograms times 9.80 meters per second squared, 123 newtons. So our weight, 123 newtons. What other force is acting on the incline? Well, we know it's on a surface, and anytime we've got something on a surface, there's going to be typically a normal force. So what direction is the normal force? It's not upwards. Remember, the normal force is normal, perpendicular to the surface. So the normal force is going to be in that direction. In other words, perpendicular to the incline. Okay, very good. Now, what do we know? We know that the acceleration in the y direction is 0. There is no motion in the y direction. This is going to slide, and it's going to slide down the incline, but not in the y direction, which means if ay is 0, Fy, which is equal to may, and if ay is 0, Fy must be 0. So let's look at the forces in the y direction. What forces are acting in the y direction, or have a component in the y direction? Well, we know that the normal force is in the y direction, and it is entirely in the y direction. So the y component of the normal force, because it's lying along the y-axis, will just be F sub n, the normal force. But what about the weight? Notice, the weight is pointing straight down, which is partially in the negative y direction and partially in the x direction. So we're going to have to decompose the weight into an x part and a y part. Let me erase this, and let me draw that in. So we're going to take this vector and treat it as the hypotenuse of a triangle, and we're going to draw in a y component and an x component. There. So here's the weight, and here is the y component of the weight, here is the x component of the weight. Let me redraw this triangle a little bit bigger so it might be a little bit easier to understand. Here's the weight acting straight down here, and we want to decompose it. We want to break it down into a part that is perpendicular to the incline and a part that is along the incline. So what is that? Well, the part that is perpendicular to the incline will be this part. That's how much the weight is acting perpendicular to the incline. And we call that, whoops, I switched these, didn't I? We call this W sub y. And then we have a component that's acting along or down the incline. And that is the x part. We call that W sub x. Now let's look at this. We know that W sub y is perpendicular to the line along the incline. And we know that this is a 10-degree angle. So let me just kind of draw this over here. This is perpendicular. And this is 10 degrees. So if this is 10 and that's 90, this must be 80. That must be an 80-degree angle. And if that's perpendicular here and that's 80, this must be a 10-degree angle. So this is the same angle as that one. And you can just imagine, you could try and convince yourself that as we decrease this incline, here, let me do it like this. As we decrease this incline and keep this perpendicular, the angle between this line and the horizontal will be the same as the angle between this line and the vertical. So when this is straight down, this is directly vertical. Whoops, here. But as we rotate this up, the angle between this line and the horizontal will be the same as the angle between this line and the vertical. Okay? As we rotate that up. You can look at it mathematically, and hopefully you can convince yourself of that, like we just did with this little triangle here. But the important point is then that this angle is 10 degrees. So what do we have for W sub x and W sub y? Well, W sub x is opposite the 10 degrees, which means W sub x will be the weight times the sine of 10 degrees, while W sub y will be the weight times the cosine of 10 degrees. Because W sub y, that's the adjacent side to the 10 degrees. So notice these are different than the components we usually have. If we have the angle defined relative to the x-axis, we usually think of the x component going with cosine, the y component going with sine. But in this case, because now we're looking at the y component relative to the vertical, it's going to have the cosine, and the x component has the sine. Great, so let's stick some numbers in here. We get then that Wx is 21.4 newtons and Wy is 121 newtons. So let's go back to the net force in the y direction. We had that F sub y was equal to the normal force, and then W sub y is in the negative y direction, so we have to subtract W sub y minus 121 newtons. And those are the only forces acting in the y direction, the normal force and W sub y. We know that the net force in the y direction must be 0, which leaves us with Fn minus 121 newtons equals 0, or, bringing that to the other side, Fn equals 121 newtons. Okay, notice, very interesting, the normal force does not equal the weight in this case. What we found was that the normal force is equal to W sub y, and W sub y was equal to the weight times the cosine of the incline angle. This is going to be something that we will see so often that it's actually worthwhile to remember this. And that is, any time that you have an object sitting on an incline, as long as there's nothing else pushing on it in the y direction, what we will find is that the normal force will be equal to the weight times the cosine of the incline angle. So whatever this incline is, measured from the horizontal, the normal force will be the weight times cosine theta, or mg cos theta. When we are doing a similar kind of problem, I will basically jump right to the result that under these circumstances, the normal force is mg cos theta. but the way it's derived is by looking at the forces in the y direction and setting them all the sum equal to 0. So let's just keep that in mind. We'll come back to that. What about the forces in the x direction? What forces are acting on the block in the x direction? What are the net forces in the x direction? Well, what forces act along the incline? Well, the only thing acting along the incline is the x component of the weight. So that is W sub x. That's the only force acting down the incline. But we know W sub x in this case is 21.4 newtons. And just again, that's kind of worthwhile to remember. Under similar problems, the component of the weight acting down the incline, W sub x, will look like W sine theta. In other words, let me just write that out. W sub x, assuming x is defined as the direction down the incline, W sub x is W sine theta, or mg sine theta. So when we need that, I will just put that down as well. But remember, this is how we determine that. Normal force for an object resting on an inclined surface with no other forces acting on it perpendicular to the incline. Normal force, mg cos theta. The component of the weight down the incline, mg sine theta. Okay, so what do we have? The net force in the x direction is then 21.4 newtons, and that must equal the mass times the acceleration in the x direction. Divide by the mass, we have the acceleration in the x direction is 21.4 newtons, divided by 12.5 kilograms, which leaves us with the acceleration in the x direction, 1.71 meters per second squared. There we go. Very, very good. Excellent. Let's take a look at a similar problem, but let's assume there's some friction between the crate and the incline. How is that going to affect our result?